Yeah, good morning to all of you. It is easy for you to understand. Okay, so don't worry about that. So, but before that, so I will ask you one of you. Mehak, are you here, right?
Yes, sir.
So I'll give you equation x minus y equal to 0. Okay. Can you give me some points on that? X minus y equal to 0.
1 and 1.
Yeah, still few more points.
2, 2, 3, 3.
Yeah, like very good. So you know that equation, just keep with you. Now, Amia, so I gave one line to you, that is x plus y is equal to 2. Okay, Amia?
Yes, sir.
Okay. Now I am giving another point to Kaustubh. Okay. So the equation is 2x minus y is equal to 1. 2x minus y is equal to 1. Okay. So now, so you all know some points on those lines, correct? So Kaustubh, what is
Yes.
your line? Okay, Shubhamoy, what is the third line? Do you remember?
No, sir.
2x minus y equal to 1.
Okay.
Okay, so three lines I gave, x minus y equal to 1 and x plus y equal to 2 and 2x minus y equal to 1. Okay, so
Yes.
I have a secret point with me. I have one point with me. Okay, so now this point lies somewhere. Okay, so now, for example, Amia and Mehak came together. Then they figure out what is the point. So now the equations given to them is x minus y equal to 1 and x plus y equal to 2. So Mehak or Amia, can you tell me the point?
3/2, 1/2.
3 by 2 comma 1 by 2 lies on both of them.
Yes.
How x minus y equal to 0
X
contains?
minus y equal to, oh, sorry.
Oh, sorry, x minus y equal to 0. Yeah. Mehak, I gave x minus y equal to 0. Yeah.
1, 1.
1 comma 1. That is the only point, right?
Yes.
What is the point common to x minus y equal to 0 and 2x minus y equal to 1?
1, 1.
1 comma 1. What is the point common to x plus y is equal to 2 and 2x minus y equal to 1?
1, 1.
1 comma. So it is a common point. But if I give only line, if you take x minus y equal to 0, then there are so many points. So you don't know that what is in my mind. Are you following? Yeah. So that is what secret sharing is. I have a point 1 comma 1, but I will not give 1 comma 1. I will give x minus y equal to 0 to Mehak. I gave x plus y is equal to 2 to you. I gave 2x minus y equal to 1 to somebody else. But now if any two of them will come together, they will get the point. But a single person cannot get anything. So 100% secure. Is it clear? Shubhamay, is it clear?
Yes.
Yeah. So how it goes? So for example, x naught is a real number, is a secret, right? Choose y naught belong to R at random. Okay. Now suppose there are n participants. Suppose there are n participants. Then we can consider n lines passing through the point x naught comma y naught, one for each participant. Is it clear? Now, if any two participants come together, then the point of intersection of their lines is x naught, y naught. This is called 2 comma n threshold scheme. So can you think of 3 comma n threshold scheme with the planes as shades? Somebody can explain why it is so? Yes, am I audible? Yeah,
Yes, sir.
yeah.
So suppose there are n participants
Uh,
and then we will consider the n planes passing through the points some x0, y0 and z0.
very good, very good.
So
So,
this will be happen if three of them comes together.
yeah, right. Good, good. So like that, it's a very simple algorithm. Hai. any three people come together, then only they can get it. Because one point is common to two planes, then the point of now they intersect in a line, not in a, so still there is there is no way. Two people together, they cannot get any information, right? So this is one particular example. Now I'm giving another example. Now points as a shares. Okay, let M be a secret. Okay, now choose t minus 1 real numbers, a1, a2, at minus 1. Okay, now we construct a polynomial, fx equal to a1x plus a2x square and so on, at minus 1 x power t minus 1. Now choose n distinct real numbers, x1, x2, xn, and compute yi is equal to f of xi, right? So in particular, you can choose this x1, x2, xn as 1, 2, 3 up to n. They are distinct real numbers, right? Then now we are putting x1 in the function f of x1, and you got y1, right? Like that, we have n points. You choose n distinct real number, so you will get n points on the on that curve, defined by this polynomial, right? Now, if t participants come together, generally t is less than n. Okay. If t participants come together, that is say t points put together, right? x1, y1, x2, y2, and so on, xt, yt. Now the dealer know the secret m, and he only know these coefficients. He will not give the coefficients. He will not give the polynomial. He only give the shares. Shares are these points. Is it okay? Amya, is it point is clear?
Yes, sir.
Yeah. Now these x1, y1, x2, y2, xt, yt, these t points to come together. But now there is a unique polynomial of degree t minus 1 passing through these t distinct points. Why these are distinct points? Because x1, x2, t are different, right? Hence, it is possible to get the coefficients of the original polynomial and the secret. This is t comma n threshold scheme, where n is greater than or equal to t. So how it is done? So you have t points, and you take any t minus 1 degree polynomial. Suppose consider t minus 1 degree polynomial. Now this polynomial is satisfying all these points. What is meaning of that? Yk equal to b naught b1 xk plus bt minus 1 xk t minus 1. So y1 is equal to, in particular, y1 is equal to b naught plus b1 x1 plus b2 x2 and so, x1 square and so on, bt minus 1 x1 x1 power t minus 1. Now you write into matrix form, right? Now it will be like this. So b naught bt1 minus 1, I have to compute. I do not know the polynomial. I want to compute the polynomial satisfying these t points, but the polynomial degree is t minus 1. Now you construct this matrix, right? Now this is called Vandermonde matrix, and we know that the determinant is equal to xj minus xy, which we done in the previous class. This can be done by using induction also, right? Since xi's are distinct, ax equal to y has a unique solution. Any questions? Are there any questions? Kaustav, are you clear?
Hello.
Yeah, are you clear this point? Okay. Amya, are you clear?
Yes, sir.
Okay.
Yes.
Yes.
Sir, can you sir, explain the scheme again, because I was just lost. मतलब मेरा audio चला.
This diagram.
Yes, scheme, sir.
Sorry, I'm not. Your voice is not that audible.
Can you explain the scheme, sir? Hello.
Yeah. Somebody can help me. What is Subhama is saying? Okay. Sorry, actually, you are telling exam scheme. Okay. Yeah. Okay. It's not visible. Okay. So Mehak, are you clear till now?
Yes, sir.
Okay. So now this is you can create n comma t scheme, right, with points as shares. Whatever t you give, whatever n you give, but n should be greater than or equal to t, correct? Okay, now coming to visual cryptography. So I told you that visual cryptography is also secret sharing scheme. It is part of secret sharing. For example, I have a message. So that is image. I love India. So this secret image, now I divide into shares. How many shares? N shares, right? Now if k of the people come together, then they can stack it and they get information. If k minus 1 or less will come, they have no information on the this one. Okay, so we discussed this, but I'll repeat. This is called again k comma n visual cryptography. So this is given by Pastor Nair and Shamir in 1994. Okay, so I will just tell you what is happening is that there is a secret holder, so dealer. So he will share the shares with n individuals. So individual shareholder. Okay. So now, so in the k comma threshold scheme method, n pieces of information of the secret key called shares are distributed to n participants, so that secret key can be reconstructed from the knowledge of any k or more shares, and the secret key cannot be reconstructed from the knowledge of fewer than k shares. I'll explain with one example. We discussed it earlier, but I'll go a little fast now. So now assume that your image is made up of white and black pixels, right? So white pixel comes, then two shares will be given like this. This white pixel can be shared with these two white pixels. Now the size of the image is increased. One white pixel now become 2 pixels, black and white, right? So the first person given this share when white comes, second person given this. So they together stack it, then they will get white and black, right? So for one pixel we can give this, for another pixel you can give this, not a problem. For each pixel you can you can toss a coin and you can give. But you can fix it only first one also, not a problem. Now it is a black pixel, then again they will make into two shares. But these two together come together, then I will get a black, right? So like that we'll give shares. But when we are giving shares, then each pixel is has white and black only. As such, they do not know any information. It is again 100% secure. But they come together only. The black pixel part become black, whereas white pixel become white and black. Okay. So because of that, it is uh, because of that, it is not 100%. There is a little contrast. Now black becomes very much black, but white become white and black. Any doubts? Please say respond. Yeah. Is it clear, or you want me to explain? Mehak, are you clear with this? We have doubts somewhere? Okay. So this particular thing I can think as S0 and S1. S0 0101 and S1 is 0110, right? So in general we have 2 comma in VTS threshold scheme. Is it visible, this brown color box? Amaya?
Yes, sir.
Is it possible to read also?
Yes, sir.
Okay. So now S0 equal to, so we take matrix like this, S1 is like this. So you can look at here that what happens if two white pixel now given to n people, right? So then what happens if two people come together, then one is white and others are all sorry, one is black, others are zero. Whereas black pixel shares comes, two are black and remaining are white. But even then it is possible to recognize the image, but there is a lot of contrast, and as n increases it is very, very difficult. Yeah, so I'll explain this with one 3 threshold scheme, right? So this is a little different one. So what happens is that white share is given to 3 people like this. Okay, if they come together, then it will be like this. Yeah, whereas black pixel is given to 3 people in this way. So they three come together, then we'll get this way, right? So in that way, now you stack it. So first three shares are like this. Okay, first three shares, white. So three people we gave like that. They do not have any information. They come together and do it, then they will get hello world. Any questions? Okay. So this is what I want to convey, little fast way, right? Yeah. So yeah, stop share now. So if you do not have any doubts, then let me. Okay. So I am starting with one simple thing that in the previous class he introduced, Kaustubh introduced hash function, right? So a little bit of it is not 100% hash what I'm going to say, but something like one-way function, right? So we are going to discuss today some problems on public key crypto system. But before that, I will try to explain you certain aspects, right? Just recall so that we'll go a little fast. So we have a domain, right? So we have a domain and we have a codomain, right? Codomain, right? Then there is a function. So so f is a function and it is easy to compute. Easy to compute. And we have, but what about this direction? Okay, so f inverse difficult to compute. In particular, it is not invertible, but here I am assuming f is invertible function. In PKC, all of them are invertible function, public key cryptography, right? So f inverse is difficult to compute, hard to compute. Okay, whereas now, whereas if you f inverse with a trapdoor information, with a trapdoor information. Okay, then easy to compute. So this is what actually public crypto system mainly depends on, right? Okay, so let us see what is that I want to say, that this function f is invertible, right? F is invertible. F is one way. One way means easy to compute. Easy to compute. But inverse difficult to compute. But inverse difficult to compute. Yeah, okay. So why this is public crypto system depends on that. So I'll give one thing, right? So in the public crypto system, PKC, right? Public key crypto system. So in the public key crypto system, we have two keys, right? One is called K public, one is called K private, right? This pair, K public, comma K private, is a pair. So this pair now comes with this pair comes with encryption and decryption functions. K public comes with EPUB function. This is called encryption function. Are you fine? It is called encryption function, and this is easy to compute. It is easy to compute. Okay, and now K private also comes with another function that is called D. So K pub actually, yeah. So dk private. So this one is easy to compute. One who knows k private, right? But this is difficult to compute. Only with k public key, only with information. Okay, so this k private act as a trapdoor. Okay, so yeah, so what is a trapdoor actually? So the trapdoor is a piece of information. The trapdoor is a piece of auxiliary information. That allows inverse to be computed easily. Yeah, any questions? Yeah, this is the main public key crypto system depends on. So we done several examples. So let us see one example quickly, right? We done it, and that's why I'm going a little fast. Okay. So for example, RSA crypto system. Yeah. So, but before that, you understand that Diffie-Hellman, when they first gave this, so they are not in a position to give the public key crypto system with a trapdoor. Means they are difficult to compute the one-way function. So at that moment, people are trying with hard problems. So these RSA, these three people gave with this RSA crypto system, but it took time. But many people tried it. Once that paper came, Diffie-Hellman paper, there is a lot of rush to get that something. And there is other persons, Merkley and Hellman also tried but they are using the knapsack problem. Knapsack problem is very hard, but they are not succeeded actually. Yeah. But RSA crypto system gave nicely. So later Elgamal came. Yeah, Elgamal crypto system. So, but they are not came like immediately, right? It took time. Now we are studying them. So we are actually describing what is exactly already there. That's why this subject is a little bit boring in one sense, in the sense that we are describing white elephants already which are there. But anyhow, but still it is interesting if you do crypto analysis and all. Yeah. Okay. So let us discuss this RSA crypto system. In the RSA crypto system, what is going to happen? So there are two people, Elias and Bob. Right? So Elias wants to send a message to Bob, right? Then what Bob will do? So there are so he has to give the keys, public key, right? So first there is a key generation. So key generation, then encryption. There are two things will be there. First, we need to create public key and private key. How the key generation will happen, right? So Bob chooses. Yeah, can you somebody tell me what Bob chooses in the RSA crypto system? First,
Two large prime numbers.
yeah, two large prime numbers. So chooses two large primes, right? Yeah, two large primes. But usually they are of the same number of digits are same, almost same. They are nearby. Okay, for example, 11 and 13. Okay, two large primes, P and Q. Yes, first they will do this, then they compute. What he will compute? Compute N is equal to P into Q, right? Then also he will compute what? Since he know P and Q, he can compute phi of N, correct? What is phi of N? So P minus 1 into Q minus 1, right? Then he choose randomly one number, right? Chooses E, comma, P minus 1 into Q minus 1. Their GCD is equal to 1. He chooses this number. Once he chooses this number, then there exists a unique D, right? So that E into D is congruent to 1 mod phi N, right? Then he make, this is key generation. So now he make N comma E. Now you can throw away P and Q if you want, okay? But we need N and E and D are important. N comma E become public key, right? And D become private key. So this is key generation. So private key or secret key, correct? Then now LIS, now encryption comes, right? Encryption comes. So now what is that LIS will do, right? So LIS download this N comma E. It is public. Anyone can download. Now she want to send a message M. Okay. So she want to send M to Bob message, right? Yeah. What she will do? Somebody can come first. What LIS will do? What she will compute?
She will compute C.
Compute ciphertext. So ciphertext is equal to what?
M raised to E.
Mod
N.
N. Because LIS knows these N and E, right? So she can compute this M power E mod N, right? Yeah, good. Now she sends C to C sends to Bob. This is a ciphertext, right? Now how Bob will compute? So M is equal to how we'll get? He has to use a private key, right? You remember? Any one of you fast? Today just recalling little fast and then I will ask problems. Yes, fast.
M power DE.
Not M power D. M is not known. No? So now Bob knows ciphertext and only ciphertext. And he already know that what Bob knows, right? Bob have
C power D.
C power D. So now Bob computes C power D. So M is equal to C power D mod N. Okay. But why this is actually this? So that is easy to check. Because C power D is equal to so yeah, C power D is equal to C power yeah, this is M power E power D. Okay, so this is M power ED mod N, right? Now we are claiming that this is congruent to M mod N. Why? Okay, so that is the question. So suppose that generally we'll assume that M comma N GCD equal to 1. Okay, so because N is known, so we can take it this way: M comma N GCD equal to 1, right? Okay. Now M comma N GCD 1, we know that by Euler's theorem, M power phi of N is congruent to 1 mod N, right? And we know that what is that we have? We have that ED is congruent to 1 mod N, right? 1 mod phi N, 1 mod phi N, ED is congruent to 1 mod phi n, right? This implies what? So ED is equal to 1 plus k times phi n. Are you okay with this? Because ED minus 1 is congruent to 0 mod phi n. So phi n divides ED minus 1. That is equal to ED is equal to 1 plus k into phi n, right? Now what is now m power ED? M power ED is equal to m into m power k times phi n, right? Mod n. So now this becomes 1 because m power phi n is 1. So we'll get m. Is it okay? Is it okay? Yes, please. Okay. So one of you can respond. Is it everything clear? RSA crypto system?
Yes, sir.
Yeah. Okay. Now I am asking some questions on this right now. Okay. One at a time. So first RSA, some certain problems, right? So question number 1. Suppose that suppose you know. Suppose okay. Before that, just give me some notations. So some notations, so that in the exam also you will be clear, right? See, this n is called, this some terminology, some names to these things, right? So n is called modulus in this RSA crypto system. N is called modulus. Yeah. What is E called? Do you remember? E is called encryption exponent. Encryption exponent. Okay, and D is called decryption exponent. Yeah. Okay. Now the question number 1 is this. Question 1. Suppose you know n and phi n also. Yeah. So before going further, so one more thing is that there are 3 persons, right? Alice and Bob, and there is another person, Eve. Okay. But what Eve knows now in this problem? What are the information Eve know? Can somebody help me?
N E
N E, correct. Ciphertext C, because it is also traveling. Now C is also public, but finding M from C is difficult. Why? Because evaluating D is very tough. Yeah, that is equivalent to the problem of factoring n equal to PQ. So those I will now discuss. Yeah, next one. This much only. Yeah, these things are known. So C is known, but also she knows that C is equal to what she know. C is equal to M power D. They know the technique. She know that it is RSA crypto system. She know M power D, and she also know that this D is sorry, M power E. She knows that this is M power E, and she also know that this we can get it once we know the inverse of E, but she cannot compute that, right? So she does not know what E does not know. Does not know D, does not know P, does not know Q, and yeah, and then automatically does not know phi of n also. Right? This is very difficult from n computing phi n also. So now I am telling you that suppose you know n and phi n, then how it is? Then it is then easy to compute. Easy to compute P and Q. Can you say why? Of course, n is equal to PQ here. Easy to compute P and Q. Why? Is the question clear? Suppose you know n and as well as phi of n. Then we are claiming that it is easy to compute P and Q. Why? Yeah. I'll give some time to you to think about. Any idea, any clue? What is it you do not know? You do not know PQ, P comma Q independently. N is known, product multiply करके दिया है. P of N is given. Yeah. So Amaya, is the question clear?
Yes, sir.
Yeah. Okay. So now I will ask you a few questions so that it will help you. Okay. So proof solution, right? So what is N minus phi N plus 1? Right? It is PQ minus, right? This is phi of N is P minus 1 into Q minus 1, correct? Plus 1. So can you tell me what is answer, final answer?
P plus Q.
P plus Q. So we do not know P and Q, but now we know P and P plus Q. Do you know P into Q? That is equal to N, right? N is known. So we know that now we know these values, right? We know N minus phi N plus 1 and we know N, right? So from these two, so that means that I have this equation, right? X power x square plus N minus phi of N plus 1 into X plus N, right? So I have this equation, polynomial. So how this polynomial now, how it is? It is x square. Okay, I'll take it minus here. Yeah, x square minus this. Yeah. Now what is this? X square minus, what is this value? This is P plus Q, right? P plus Q into X, but we don't know P and Q again. Okay? And it is PQ. We don't know P and Q, right? Now I want to, but what is this equal to?
X minus P into X minus Q.
This is X minus P into X minus Q, right? So P and Q are actually what now? The roots of this polynomial, right? Finally, so P and Q are roots of the polynomial. So I'll simply call this value, this is equal to say some S, right? Yeah, some S, okay? So P and Q are the roots of the polynomial. Roots of the polynomial. X square minus S into X plus N, right? So how do you find the roots now? You know the formula, right? So P comma Q is equal to congruent to plus or minus, right? So it is equal to, so S plus or minus root of B square minus 4AC, so 4N by 2A. Right? From that you can get the P and Q values. Is it part is clear? Mahek, is it okay?
Yes, sir.
Yeah. So what is that we proved? If I know N, PQ and N and phi N, then it is easy to find P and Q. Any questions? Any questions? Okay, no questions. Okay, good. Now I am asking you that question number 2. We should not take E is equal to 1 or E is equal to 2 as exponent, an encryption exponent y. Yes, can you suggest me? Easy actually. This is very simple problem.
E is 1, then even D will be 1.
Yeah, E equal to 1 implies D equal to 1. So then what is that ciphertext?
Same as plain text.
C is equal to M power E, right? Mod n. So C is equal to M only. So there is no change. There is no encryption at all. So E equal to 1 cannot be taken, though why E equal to 2 is not taken? Because we are looking at RSA crypto system, N is equal to P into Q. What do you know about N? Can it be even?
No, sir.
N cannot be even. Why cannot be even?
It's a product of two odd primes.
So it is very easy to know when it is even, then one of the prime is 2. So very obvious. So then what do you know about phi of N?
It is even.
Phi of N is even. So phi of N is even. So you cannot take 2 comma phi n is GCD is equal to 2, not 1, right? That's why we should not take equal to 2. There are high chances that T is equal to 3 will be taken. Yeah. So when generally we need to compute two things now. What are the things we need to compute? Encryption function and decryption function. When they become easy, when encryption is ciphertext we are computing, that is equal to what? M power E. If E is small, then computation becomes easy, right? Decryption function evaluates C power D. If D is small, it is easy. But both C and D cannot be small, E and D cannot be small simultaneously. One is small, other is large. So people tried that, this technique also. But they realized that D is small, then again there are problems. Okay, you can explore that, but I cannot explain that because that depends upon the continued fractions. If D value is less than less than n power 3 by 4 something square, then it is very easy to compute n and pq also. Pq computation becomes easy. So because that n D has to have some fixed length. It is greater than some length. That is known. Okay. So that problem I'm not solving today. Yeah. So, but what is that? I want to say that many people take E equal to 3. Most of the cases, people take E equal to 3. That will work nicely. Look at another aspect also, right? My C is equal to now M cube, right? M cube mod n, right? So actually, my M is equal to actually cube root of C. But this is not that easy. Okay, that is the crux of the problem. Yeah, this is not that easy to compute. One can prove that this is again difficult to compute. This is equivalent to compute product of factorizing n. That is a tough problem. Yeah. So I'll ask more questions now. Okay. So some start with simple questions now. Okay. Question number 2 is that. So I gave you n is equal to 11413. Okay. And I am giving you that this is equal to 101 into 103. Yeah. So now C is equal to ciphertext. If you want, you can use the calculators in the exam also. 7467. This is my ciphertext. Sorry, exponent. This is the exponent. E value. Encryption exponent. Since it is a small number, I am able to factor it. But in general, you do not know this, right? So ciphertext is given. C is equal to this is the ciphertext I am giving you. Okay. So find the plain text. Is the question clear? Is the question clear?
Yes, sir.
Yeah. So this is problem number 2, right? Yeah. So start working. So tell me the how can you do it? Yes, please. Sorry.
So we can start by computing D.
Yeah.
So
Yeah.
that
So
is going to be
so we need to compute D, correct? So goal is to compute goal is to compute D. Okay, here I'm giving you. So D is equal to 3 only. Okay, so that is 3 is congruent to 7467 inverse modulo 1141. Sorry, Euler phi function, right? What is modulo phi n, right? What is modulo phi n? Easy to tell. 10200, correct? Yeah, so this is you can compute, but now how can you compute the plain text now?
Power D.
So ciphertext is this, right? So what is that? You can give me answer now. M is equal to plain text.
5859 to the cube.
5
Modulo n.
power 3 mod n. So n value is 11413. 11413. Right? Yeah. So this is now going to be, if you compute it. Yeah. So answer I'm giving you. So this is 1415. Yeah. So 14 actually no, n, right? In the alphabets. This is O. No. Answer. So message is no. Okay. Is it okay? This problem is fine.
Yes, sir.
Now question number 3. I will ask another question, right? First, I'm starting with simple questions so that so I'm giving you n is equal to 55 and e is equal to 3. So find d. Yeah. So simple question. So can you try it? Very simple. So n is equal to 5 into 11. So phi of n value is equal to 40. Right? So your goal is congruent to 1 mod 40. That is easy. Yes.
27.
Yeah. So 27 into 3 is 81. So 81 is congruent to 1 mod 40. So D is equal to 27. Right? Okay. Mahak, is it clear till now?
Yes, sir.
Okay. Now I'm giving you ciphertext is ciphertext. Question number 4. Ciphertext equal to 75. That is C value. Right? I'm also giving you E is equal to 3. Okay. So we know that the plain text is and also n value is n is equal to 437. Yeah. So we know that plain text is 8 or 9. We know that answer beforehand. Okay. We know that plain text is 8 or 9. Okay. So plain text is 8 or 9. Yeah. So then from this, but without actually, without factoring n, can you find the plain text? I hope question is clear. So ciphertext is given, exponent is given, n is given, right? We also know that the plain text is 8 or 9. Forget about that, right? But we can use this. Plain text is given. We know that it is 8 or 9, but I want to check which one is. How do you proceed?
We calculate 8 cube and 9 cube.
Right. We'll calculate 8 cube and 9 cube and it is equal to ciphertext or not, right? So if you compute 8 cube, so which is congruent to 75 mod 437. So, yeah. So that is, we can compute this. Similarly, 9 cube if you compute. So 9 cube if you compute, you will get not 75, some 292 you got, 272, 92. So mod 437, right? So now plain text is 8. Any questions? So I starting with a simple problem so that you will be comfortable. Yes. Yeah. Okay. So any questions, please? Right. Now I'm going to another problem. That is a question number. How many I completed? 4. It seems 5. Huh? Question number 5. Question number 5. Okay. So the problem is that how to decrypt. How to decrypt. How to decrypt. How to decrypt. What is decrypt? C is equal to m cube mod 101. It is given. Okay. So now you need to decrypt it. But so 101 here, 101 is prime. Note that point. So can you decrypt it? No need to give exact m value. Anyhow, m is not known, also c is not known. But how do you proceed? Right? So are you there?
Yes, sir.
Yeah, this is n, right? What is phi of n?
100.
100, right? What is the GCD of 3, 100?
67. We can compute c power 67.
3, 100 GCD is 1. So now 3D, this is E, right? 3D is congruent to 1 modulo 100. Right? What is D, right?
67.
You can check that D is equal to 67, right? Okay. 67 into 3 is 201, so it will work, right? So 3 into 67 is equal to 201, right? So now what is the m value now? M is equal to c power 67 modulo 100 modulo 101. Yeah, any questions? Okay. So you have to tell something. So not easy, but or if you have doubts, you have to ask me. Mehak, are you have any questions? Is it completely clear? Suresh?
Sir, it's
Yeah.
clear, but 101 is a prime, which is our n. So n should be some p into q.
But in this problem, I even not given product of 2 prime. Single prime, what happens? Okay. So
Okay, sir.
we can work, but that is not, we can easily crack everything. Yeah. But so because we can use Fermat-Still theorem and all things becomes easy. Yeah. But it is just given that how to compute D and all to understand. Yeah. So in general, it is not related to RSA crypto system. RSA crypto system and should be P into Q only. Correct. Yeah, agreed. Okay, now I'm giving another question. Nice question. So it is very interesting. So this is what I'm telling that attacks, right? So choose a ciphertext attack in RSA, how it is, and I'm telling you. For example, Alice and Bob. Okay, listen question carefully. Alice and Bob agrees Alice and Bob and Eve are there. So of course, Eve is the want to get the information what Alice and Bob are sharing, right? So but Bob agrees to decrypt. Bob is a decryptor. Bob has a private key. Yeah, Alice is sending message to Bob. Alice is sending message to Bob, and Eve want to know. But Bob agrees to decrypt some message. Okay, some message that is called chosen plain text, right? Some message of Eve. He agreed for that. That is called chosen plain text. Who choose the plain text? Huh? Who choose the plain text?
Alice.
Alice.
No. Plain text original is there, but now Bob agrees to decrypt some message of Eve. So chosen plain text attack, right? So chosen plain. Yeah. So Eve choose this, and Eve give to Bob to decrypt. But from that now original message can be known or not. How the Eve is a very intelligent guy. How he can choose this one? So that is the question. I'll explain you what is that I want to say. In particular, I will give you the plain text also. What Eve will give to Bob. Okay. So now, um, so for example, what Eve knows. Okay, before discussion before actually giving the problem discussion. What Eve knows actually.
Plain text M.
No, plain text Eve does not know.
Oh, sorry. Encrypted message.
Okay. But before that, public key also, public key, right?
Yes.
So she knows N, E, and C, ciphertext, correct? So these three she know. But what she want to know?
M.
She want to know M. She want to know M. Okay. Yeah. But what Bob agreed? What Bob agreed? Bob agreed to decrypt some plain text given by Eve. Okay, what Eve will give? So Eve is giving this plain text. Listen carefully, right? Eve is giving 2 power E into C to Bob. Okay. Now Bob will decrypt and give it to Eve. From that, Eve get the M. How? Is the question clear?
Yes, sir.
So because it is chosen plain text attack, so Bob allowed, I am ready to decrypt one plain text. Okay, Eve is very intelligent. She chose E power 2 power E into C. How she can compute? Because she know E. Okay, she know E and all. So mod n, of course, mod n. So she computed this and give it to Bob. Okay, what happens? What Bob will give you? Can you compute now?
So 2 power ED into C power D.
Yeah. So Bob computes. Actually, we can think of little complicated here, which is plain text, which is ciphertext. Okay, actually, it is a ciphertext. Now Bob is giving the plain text, right? Am I correct? Are you okay?
Sir, can you repeat?
It is actually Bob decrypt. When Bob do decrypt, what is the text he will get usually?
Ciphertext.
Bob. When Bob will do decrypt, what he will get?
C.
Main text, right? See, try to understand. So see what Bob will get generally. Forget about this business. In RSA crypto system, what Bob will get?
He'll get the encrypted message, or
No, he will get from allies, but finally when he apply the algorithm, what he will get finally?
at the end when he decrypts, at the end he'll get M back.
M, right? Yeah. So he's that means what is this decryption algorithm is doing? What is input and what is output?
Input is C and output is M.
Yeah. So that bit input is ciphertext and output is the plain text, correct?
Yes, sir.
Yeah. So these are very little this one. So now that's why I'm telling it is a chosen ciphertext. So Eve is giving the ciphertext. Okay. So and Bob is giving the plain text. Now is it okay or okay? Not okay. So the plain text and ciphertext are from the same, so that's why it is little complicated, but actually it is ciphertext. Bob agreed to decrypt some ciphertext. Are you okay?
Yes, sir.
Yeah. So decryption algorithm always decrypts the ciphertext and gives the plain text, right? Now you are correct. Now what is that Bob will get? Bob will do. So Bob will take the ciphertext given by Eve, right? Generally Alice will give, but now Eve is giving. He knows that. So he agreed to give that. So 2 power E C power D. So mod n he will compute. Now can you tell me what is its value?
M.
M, right? No, not M. So be careful.
2M.
2M. Okay. So this is equal to 2M mod n. So now Eve knows. Eve wantedly gave that. Now Eve knows these things. Eve knows E, N, E, and of course by using N, E, and what is that? C.
C.
From these only she actually computed this ciphertext, what she want to decrypt. Already this is there. Okay, now she knows from the Bob agreement, she knows 2M also. How do you get now plain text? So 2M by 2. Right, she will divide it by 2. That's why she choose it to. Is it clear? Not clear. Any questions? Mehak, I think you are confused.
No, sir.
Everything is clear?
Yes, sir.
Very good. Thank you. Yeah, please respond. Huh? So Amaya, are you fine?
Yes.
Yeah. Okay.
So I'm just thinking a bit.
Okay. Yeah. So you need some time. Okay.
Yes. Sir, but here, so we cannot, can we directly write 2M by 2? Because dividing by 2 mod n means like.
No, Eve knows actually this is final result she is going to get is even. She knows that.
No, but it could happen that 2M is more than n.
But modulo she will do. Yeah, okay. So you can figure out what is happening. So it is quite obvious to get M directly from here. Okay. So she will know C2M, then she know that I have to divide it by 2. If
but
you
I'm saying 2M can be odd as well.
2M can be odd. Okay, when you do modulo n, right? That's what you are telling.
Yes, sir.
Yeah. By 2 actually meaning is that inverse of 2 only. Modulo n.
Yeah.
That is not a problem. Yeah. Okay. So now another question is that. Okay. So another question is that what happens if we do the double encryption? Is it the strength of the RSA crypto system improves? These questions are interesting, right? So you people try to understand that This course will be interesting when you do the more and more analysis. Very nice subject. But for that, you need entire number theory. In particular, when D is given, how to find N? You need to use the, if you are interested, I can tell that, but it takes time. So first we need to introduce continued fractions. They will use all the parts of number theory. Okay. So now coming to next question. So question number 6, 7. Question number 7. What is that here happening is that first I will have C1. Okay. So C1 is constructed from m power E1 mod n. Okay. So that means that E1 comma phi of n GCD is equal to 1. I also have E2. E2 comma phi of n GCD is also equal to 1. Right. Now I am not sending this to ciphertext to Bob. Okay. We are not sending this as it is. What we are sending, we are doing again one more time. What is that we are doing? We are doing now this C1. I'm computing C2 from C1. It is equal to now this C1 is M now, but now the encryption exponent is E2. So that is C1 power E2 mod n. Is it clear?
Yes, sir.
What is C2 now actually? Final answer. C2 equal to what?
M power E1.
M power E1 E2, right? Mod n. Okay. Is it improving? That is the question. Is it the same or is it improving? Okay. Look at what is that we have. E1 comma P of n GCD is 1. E2 comma phi of n GCD is 1. Right? Yeah. Can you say something now? And is there an improvement or not? Comment on that.
E1 E2 will also be co-prime to phi n.
Even E2 also co-prime to n, right? Phi of n is 1. So it is actually again, it is a ciphertext again. So even E2 is another E exponent. So there is not much use. Okay, it is as same as the, it is same complexity as the original. Are you okay?
Yes, sir.
Yeah. So people think that okay, I'll do 2 times, 3 times, 4 times, then my it is will be tough, easy. No. Final thing is that we don't worry about Bob do not know how many times he done or whatever, right? So only thing they will only thing here is that for even need to changes, these two together are doing. So that D1 E1 के लिए D1 होगा, E2 के लिए D2 होगा. So D1 into D2 he will do, right? So like that things will come. Yeah. Okay. So but it is same, not much complicated. So you need some time. Are any questions? Okay, good. So now I'll ask another question. So question number 8, right? So actually why we need to compute, this question is about why to compute phi of n. Is it okay to work with? And before the problem I'm telling, is it okay to work with half phi of n? Okay, that is a question. So I'll tell you now. Yeah. So to tell you the problem actually. So I have n is equal to p into q. So what do you know about PQ? Where P and Q are odd primes, right? That means n is odd. Do you know that is it has a primitive root modulo n? Do you remember something? primitive roots last semester.
Yes, sir. It will not have primitive roots.
Yeah, see, we know that a number n has a primitive root. N has a primitive root. N has primitive root if n belongs to what? 2.
Power of prime.
Yeah, 2, 4,
Power
k,
of prime or 2 times power of an odd prime.
right? Where p is an odd prime. But now p into q both are odd, then it will not work. This we know from our earlier. That means that this un is not cyclic. Okay, and then instead of en, I can work with, but now exponent. Every abelian group has an exponent. So exponent of un, okay, divides half en. That is our goal now. So that means that I can work with this. So that is the point. So I'll tell you now one after the another all these things. It is a out sketch before giving the problem, right? Before giving the problem, I told all of the things. So now, so now that exponent also comes. So since I discuss sometimes, so I am telling these things beforehand. But those who are not done, we can work independently. No, the problem is given like this. So suppose x comma n GCD is equal to 1. So now prove that x power half p of n is congruent to 1 mod p. Prove this. Is it okay?
So where n is equal to pq, right?
N is equal to pq. Yeah. So this is number 1. Yeah. So number 2 is that x power half times p of n is congruent to 1 mod q. So there is no discrepancy between. So third part is that x power half p of n. Actually, this is our goal. Actually, congruent to 1 mod n only directly. These are easy. You can tell now. How can you prove that x of half p n equal to 1 mod p? So we know something. So x comma n GCD1 implies what you know about x comma p GCD and x comma q
One.
GCD. Yeah. Right?
Both of them are 1.
Both of them are 1. That part is known, right? Yeah. So now coming to these questions, right? So x power half times phi n, okay, which is equal to x times x power p minus 1 power q minus 1 by 2, correct? Is it congruent to 1 mod p?
Yes, sir.
Yes, right? By Fermat's little theorem, x power p minus 1, x comma p GCD1, then x power p minus 1 is 1. So we have this, correct? Yeah. So is it okay, Mehak? Or some questions? Suresh?
So it's okay.
It is clear, sir.
Clear, okay. Now, so similar lines, you can prove that. I'm telling one more time. So P of n, which is equal to x power q minus 1. So phi of n is n equal to p into q. Phi of pq equal to phi of p into phi of q. So because we are assuming p is not equal to q. Yeah. So this is equal to, is it recording happening? Yeah. Okay. Yeah. X power q minus 1 power p minus 1 by 2, right? So it is equal to 1 modulo q. Yeah. Now, how do you prove from these? Now you have that x power of n is congruent to 1 mod p. X power half n congruent to 1 mod q. So from these two, how do you prove that x power of n is congruent to 1 mod n?
Chinese remainder theorem.
Or in fact, so you can easily see that now from this p divides x power half phi n minus 1, and q also divides x power half phi of n minus 1, and p comma q GCD is 1. They are primes and distinct, right? This implies that the PQ also divides, right?
Yes, sir.
That can be proved easily. So we done it several times. So it is equal to n divides x power half of E of n minus 1. Okay? So with this, you can easily see that I can work with ED congruent to 1 mod half phi n only. No need to work with that. Like that, you can decrease. In fact, that's why people instead of working with this one, they work with lambda n. You know, you remember lambda n? Carmichael number. It is the exponent of un. You no need to work with phi n. You can also work with lambda n, right? So that's why it is very interesting. So uns are a billion, even though they are not cyclic. So we have exponent. So these are interesting problems. So very, very nice to. So those who are done number theory course, so for them, cryptography becomes very, very cakewalk and very interesting. Yeah. Any questions to ask? Yes. Yeah, please respond. So is it okay? Till now clear everything?
Yes, sir, it's clear.
Okay. So can you take a small break for five minutes? Then we again will start half an hour, another few problems. This is continuously we are doing. What do you suggest? Or you want me to complete? So, okay, take a small break. We'll again meet. Okay, let me share again. Right. Yeah. Yeah, few more problems on RSA crypto system, some problems, right? Yeah. So few more problems are like this, right? I gave you this part. Yeah, so sometimes we should be careful. That is my question. So, so can you give me the number n equal to such that phi of n is equal to 24, right? In RSA crypto system only.
35.
35. Okay. So that is question number 9. I'm discussing now with you. So question number 9. So yeah. So when phi of n is equal to 35, it is a very small prime. So it is equal to 5 into 7. So phi of n is equal to 24, right? Now, what are E I have to choose and what is the D I have to choose? Now you know that E belongs to where? E can be 1, right? I cannot take 2, 3, 4, 5, 7, 8, 9, 10, 11 can be taken. 12 I cannot take. 13 I can take. 14, 15, 16 I cannot take. 17, 19. So 20 I cannot take. 21, 22, 23. Yeah. So all of them are primes. 5, 7, 11, 13, 12. Because 2 into 3 is there, right? Yeah. So 2 into 10, 15. So 5 multiples has to be taken, but 5 or 7, right? But the immediate multiples are 14 and 15 or 10. Those are co-prime, not co-prime with 24. These are the numbers. Total 8 are there, correct? Yeah. Now, now you can see that these are pairs, right? 1 comma 23 are inverse to each other. Okay. Of course, additive inverse, right? That is what I want to say, that 23 is congruent to -1 modulo 24. So if I square them, so 23 square is congruent to 1 modulo 24. 1 square, right? 1 square modulo 24. So like that, these are paired, right? 9 is paired with 29, this one, right? So these two are paired, right? And 7 and 7 and 17 are paired, right? And so 11 and 13 are paired, right? So like that, these are the paired. So now in order to compute inverses squares, right? What is it I have to compute? It is sufficient to compute for some numbers. What are those?
Can you repeat the question?
The question is that in order to find squares of all these numbers, 1 square, 5 square, 7 square, 11 square, 13 square, 17 square, 19 square, 26 square, it is sufficient to compute what?
Squares of half of them.
So 1 square, 5 square, right? 7 square and 11 square. So is equal to what? 23 square, right? 19 square, right? 17 square, and 11 is related to what? 13 square. So these are same, right? So it is sufficient to compute these things, right? But what do you know about these things, right? X square is congruent to 1 modulo 24. 1 modulo 24. Yeah. Are they satisfy this equation? What is 1 square? 1 square is congruent to 1 mod 24. 5 square is congruent to 1 mod 24. 7 square is congruent to 1 mod 24. 11 square is congruent to 1 mod 24. Correct. In fact, all of them are solutions of this equation. So what is the E inverse then?
E itself.
E itself, right? So that is very easy. So my point is that if somehow you able to know that, of course, you do not know a priori that E inverse is E or not. Yeah. So, but these are also some of the problems we need to think about. Okay. In this case, E is equal to E inverse is equal to D, right? So we should be careful by taking n equal to 35 or any other number, but E equal to E inverse. That may happen. Yeah. Okay. So means elements of order 2, right? In particular, elements of order 2. Okay. Now one more question I'm giving. This is just informative question, actually. Question number 9. Yeah. Question number 10 is that so Eve knows, right? Eve knows these things, right? N, E, and C. We know that part. Want to know M, right? Want to know M, right? So, but Eve observed that, but somebody gave that M power psi is congruent to 1 mod n. Are you following this part? She want to know M, but somebody gave that to Eve that M power psi equal to 1 mod n. So he gave psi to Eve. Are you okay? Hello, are you there?
Yes, sir.
Yeah, so he gave this, okay? This much is given. And also, once then Eve observed. Then Eve observed. Oh, Eve capital letter I had to put. Yeah. Then Eve observed that E comma psi equal to 1. GCD is 1. Then what she will attempt now?
She'll use the Bazoo's theorem.
Yeah, yeah, but first of all, she can compute now. There exists a unique T, right? So that ED is congruent to what?
1 mod pi.
1 mod, 1 mod,
Pi.
1 mod psi.
Okay.
So Eve, Eve does not know phi n. Somebody gave psi that m power psi equal to 1 mod n. So that much is given to her. Somebody gave that. So because she does not know m, assume that Bob itself, Bob provided this extra thing to her. Okay. He is challenging. I'll give psi, right? Yeah. Such that this happens. Yeah. So now, Eve now then observed that E comma psi equal to 1. He observed. She observed that Eve observed that E comma psi equal to 1. She computed D. Now what she can do now? So from this, it is easy to see that ED is actually what? ED equal to now from this congruence.
1 psi k plus
1 plus psi k for some k, right? For some k. Right? Yeah. This much she knows. Now what she will do? Okay. Now she will compute this D. Now Eve knows D, right? This D coming from modulo psi, not phi of n. What happens? Let us work out this. C power T. But she does not know what is C, correct? But she is computed by m power E. She knows E, but she does not know M. She know only C. So it is actually C power D only. She does not know ingredients, but even though she know E, but she does not know M. Are you okay? Yeah. So power D, right? But this is equal to what? So this is equal to M power 1 into M power psi k mod N. But what is somebody gave? Bob himself gave M power psi equal to 1 mod N. Then what happens? It is equal to M mod N. Are you okay or not okay? Any questions? Are not clear? You can ask me.
Yes, sir. Clear.
It's clear, right? So what is the conclusion of this? So if you, even if you do not know phi n and then p and q, if you able to know one psi, such that m power psi equal to 1 mod n, of course it is not 1, of course. So if you able to know some psi, then it is possible to find m. Okay, this d need not be that d. Yeah, so these are the some of the things we need to understand. It is because any multiple of m for phi n multiple also will work, right? Yeah, okay. Another question is that, yeah, but before that, other people, what about Suresh and Mehak? Are you clear with this?
Yes, sir.
Yes, sir.
Yeah, good, nice. Now I am giving another question. The question is that there are two users. Okay, two users. They are using N1 and N2. So two users using N1 and N2. Okay, both are using N1, N2. So these are the moduli. What is a crypto system? RSA crypto system, right? But they know that that means that N1 equal to P1 E1, right? N1 is equal to P1 into some Q1. N2 is equal to P2 into Q2, right? But they know that somehow we know that N1 comma N2 GCD is not equal to 1. Then easy to crack. Why? A very simple question, in between. Yeah. So can you come up?
So if N1 and N2 are not co-prime, then P1 must be equal to P2 or Q1 must be equal to Q2.
Yeah. So one of the prime, common prime will be there. Then they will know entire all P1, P2, right? This implies N1 comma N2 GCD. Okay. So can be P1, but also I'm telling you, I forgot to tell one point that N1 not equal to N2. Otherwise, this is a problem, right? N1 not equal to N2, then this is this GCD now belongs to, right? This GCD now belongs to, so P1, Q1, P2, and Q2, right? And that is also, so that says that two of them are equal. So it is possible to find, all primes. Are you okay? See, once you know, we already have N1 comma N2. Yeah. Now we know, suppose we know P divides N1 as well as P divides N2. Then what you know? So we can find N1 by P and N2 by P. So we'll get other primes, right? So, right, we'll get other primes. So we'll get all the primes now. Is it okay? Is it problem is clear?
Yes, sir.
Yeah, good. Very simple, but I want to discuss. Yeah. So like that, very, very nice problems. Yeah. Now it is another interesting problem. Very, very nice problem. Okay. Suppose now that, sorry, I'm not giving like a problem, right? I'm explaining directly because to reduce the time. Okay. Question number 12. I'm explaining the problem, not giving as a problem, right? So suppose that n is the moduli. Okay. Both Alice and Bob are using same n. Is it okay, Suresh?
Yes, sir.
They are using the same n. Okay, is the first one part is okay. So both are using same n, that people came to know. Now, what happens is that some person called Charles want to send same message n to both Alice and Bob. Okay, so then automatically, since they are using this, they will create EA exponent and EB, right? That means the public keys are ENEA. This is public key related to what? Alice. And what is a public key related to Bob? N comma EB. Yeah. Okay. So now Charles is one person. You want to send the same message to both Alice and Bob by using them, right? So what is that what is that CA? What is ciphertext sending to allies? Same message, but now exponents are different, right? Can you tell me what is that he's telling? He's sending to allies ciphertext
M power EA.
M power EA mod n, right? Same mod n. What is that he's sending to Bob? Yeah, Mehak.
M power EB.
M power EB mod n. Now Eve is observing all these things. Eve is observing. Yeah, Eve is observing all these things, and Eve is observing all these, and she noticed that EA comma EB GCD is 1. She noticed that EA comma EB GCD is 1. So question is, can Eve get M? Is the question now clear? Instead of giving question, I'm explained everything. So same module both Alice and Bob are using. And then of course different exponents. N comma A Alice public key, N comma B Bob's public key. So some person Charles want to send some same message to both Alice and Bob. So he computed the encryption messages, M power A, M power EB. But Eve is observing all these things, and she noticed that EA comma EB GCD1. Then from this information, can she know M? That is the question. What is your response?
Yes, sir.
Oh,
Again, we can use the same idea as before.
yeah, but here EA comma EB GCD is 1. What from that you can do?
So again, we can let's say that A is bigger than EB.
Okay.
So we can write EA is equal to Q times EB plus 1. And then like
Yeah, but this is another way, a simpler way is there, right? See, E power A into E power B GCD1 implies what? What is that you remember immediately?
some X times EA minus Y times EB equal to 1.
There is some R comma S belong to Z such that EAR plus EBS is equal to 1, right? Yeah. Now EAEB are given. So she knows C1 and CA and CB she knows, right? She want to compute. So let us write down what she knows, right? Eve knows. Now Eve has N, E, CA, CB, okay, and EAEB also. Yeah. Okay, let us write properly. So Eve now knows this information. EA, EB, CA, CB, and also she observed that EA comma EB GCD1. So this helped us to find out R comma S, that EAR plus EBS is equal to 1. She noticed up to this extent, right? Now M power 1 is equal to M power EAR plus EBS, right? Yeah. So this is equal to what? M power EA R, right, into M power m power EB power S. Now see, from this she also knows now R comma S also, right? So what actually she is doing to get M now, right? Can somebody help me now? So this part is okay now for you, right? But actually this is I gave the answer, but what is actually Eve computing?
CA power R into CA power CB
So
power.
Eve is computing CA power R into CA power S, she is computing. Yeah. So CA is, you know, that this M power EA power R. So now that is 1. This is 1. So she is getting this is equal to M now. Yeah. Since she knows CA, she knows CB. And so she knows R, she knows S. So she compute this and she'll get M. Is it a question is clear? Yeah. Okay then. So I'll stop today. So I gave several problems on RSA crypto system. In the next Tuesday, I will tell you some problems related to other crypto system or other things. Yeah, maybe that may be the last class. I'm happy to discuss with you, but yeah, I can do both. I can stop also. I can continue also. So it is all depends on you. If you are able to do more problems, then I will not. You can continue. Yeah, but at least one class I will take. If there is any problem on next Tuesday, then I'll take next Thursday. So I'll let you know beforehand, or we can take some other time. Yeah. But one class I will take for sure. Yeah. Any questions?